Go down, down, or down, keep going. Even more. Keep going. Force the button.
Oh, you want to see the last graph? The sine cosine?
Where's the sine cosine graph?
That doesn't look right.
Yeah.
It doesn't look mine.
It should be more jagged. So I'll take a look at and see why.
It's randomized. It moves.
Yes, but it still should be more jagged.
Oh.
It can't be. Well, you only have one, two. Well, I don't know. This only has 5 points. I have to see what I asked for. I mean, you only have 5. It looks like you only have 5 points.
Mm-hmm. Yeah,
So let me see what
m equals 5.
That's what I asked for. M equals 5. N equals 10. So each curve should have 10 points on it.
I flip them.
And let me verify that.
I guess Janet and I both flipped them.
All right, so you can see that this here says an M by N matrix. And all right, I can give some background to this. This is also a thesis problem. This is Hunter's thesis problem. I don't know how much we're going to do with this, but Hunter has a fast algorithm for computing intervals that uses a special fast algorithm. And one of the special characteristics of this algorithm is you don't need a whole function, but you just sample it at certain points. Now that's how trapezoid works too. If you just take the function at certain points and you estimate the interval. The trapezoid rule is horrible. I mean, it's very inaccurate. This method is extremely accurate. And there are more accurate methods, but what makes this special is that it's very accurate and the sampling rate is very low. And I think that's quite unique. So we've been working on this. So the reason for constructing this is we want to construct a bunch of functions to test this algorithm on. Just like for Bernoulli trials, we created a matrix of doctors to test our algorithm for detecting doctors. In this case, we're going to create a matrix of functions to check this numerical integration scheme. Now, the problem with sampling your function is if the function is too jiggly, there's nothing you can do, right? If I sample my function, if I have a cosine function like this, where is it? Oh. If I have a cosine function that looks like this, right? And if,
Slow load speeds.
yes. I will be eternally grateful to Cavendish.
I'm glad it's just not paint anymore.
I found something called smooth draw, which is quite good. It's a lot better. But okay, so if I have a cosine function like this, and this is time. Now suppose I sample this function here, 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 and here. So I'm taking regular samples of the function. Now, that's the only information I have about this function. No other information. That this function is 0 here, 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 here. That's the only information. What am I going to estimate the interval to be? I mean, if this is the only information I have, this, how can I tell the difference between this function and 0? I can't. So this shows the limitation of sampling. There's an intrinsic limitation in sampling that if the function has too high a frequency, you can't you can't possibly get an accurate estimate of the image. So you want to deal with functions that have some limited frequency. So what you generated was a bunch of functions that have limited frequency. That's what this, so I can say, okay, it's impossible to generate, to accurately integrate. A sample function if the function has high frequency. You just can't do it. So we want to limit ourselves to functions with low frequency. Now, I realize that I'm giving you very, very sketchy idea of what's going on here, and there's a lot of details I'm leaving out. But I have to tell you that in the practical working world, that's the norm. It's normal to not know everything about what you're trying to model. You have some partial knowledge, and you try to gain as much knowledge as you can to be able to effectively program. So you may feel uncomfortable and feel that you don't completely understand this, but suck it up. This is the real world. Okay, I can make a choice. I can give you sandbox problems that you can do and you understand completely, and that's useful. Or I can give real world problems that I'm actually going to use. So I chose the latter. I may give you some sandbox problems towards the end of the semester, like differential equations, because those are so important. So I may do that. But for now, I'm exploiting you to do things that I want to get done in my research. And maybe if you like this, you'll be interested to do something similar on your own. Okay. So let me just relate that to here. You can see that here's this vector called freq vec, and it's between -0.5 and 1/2. So you can see that the freq vector does correspond to the frequency, and it's limited. Now, what does negative frequency mean? I'm going to punt on that one. I have to explain some things about complex frequencies, so I can't go that much into it. Suffice it to say that this gives all the frequencies less than half. Sorry, I couldn't say more. But if you remember waves, they have frequency and phase. So I have a frequency and a phase here. And so here what you're doing is you're constructing if you remember, if you have a trigonometric function, you'll have like cosine or sine, and you have cosine of 2 pi times the frequency times time plus the phase. I don't know if you remember that, but if you think back in high school and talk about parent functions and things like that, you probably had something about phase and frequency of complex of cosines. I don't know. Do they still teach that in high school? We got? Okay.
Is there a better way to get the end? And I created a new vector for 1 through 10.
No, I don't think so. I think that's what you would do.
Okay.
I do think that's what you would do.
Because you didn't say to create that vector or anything.
Okay. Well, you could create it on the fly.
Yeah, I did.
You don't even need to define it as a variable. You could just when you create this matrix, you could just create it there.
Okay.
What is it? A range or something like that, right?
Right.
And you just say f vec times a range, and you get this thing. Okay, so what you're doing here is you're creating a let's see. All right, so you created a matrix. Each row of this matrix is a different cosine with a different phase and a different frequency. But the frequency is limited and the phase is 0 to 5. And you're adding these together. Why? Because when you have some random function, it's going to be some combination of different frequencies all jumbled together. So this is a way to generate a jumbled function that we can use to test our integration algorithm. So this is just one. This just generates one function. We would do this hundreds and thousands or maybe millions of times to see how accurate the algorithm is on different functions. Do I need to say anything else about this? So because the frequency is 1/2, I know that the fastest it can go is between two samples. Fastest it can go is half a period. So it could go as fast as half a period, but it can't actually reach half a period. It can go up to half a period. And there's a mathematical theorem that says if the frequency is less than half, if the sampling is less than half a period, then you can reconstruct your signal from the sequence. But since the maximum period is, since the minimum period is 2 samples, you probably should see, over the course of 10 samples, you should probably see something like 3-4 periods. And that's why I knew that this was not right. So we can fix it.
But wait, it says, hold on, if you go up, it says create frequency vec
Yeah,
with M entries.
yes,
With 5 entries.
yes.
So you're going to have, if frequency and phase vec both have 5 entries, you're going to have 5 points.
Well, and that's five rows, but you have 10 columns.
You're multiplying it by n.
Yeah,
which is
okay.
10.
So let's see if we can debug this.
So you should be coming up with a 5 by 10.
And then you're summing you probably summed the wrong way. That's all. I think you
Possibly.
somebody sent me something. Janet summed the wrong way. So you probably just did the same thing she did. Let's see where your sum is. All right, now, yeah, this is the deal. When you did your sum,
You sum across.
you sum down. You sum down. I don't know if that was clear in the description, but take the sum of rows, not sum across rows. Sum of rows.
Okay.
All right, I can see how you would. I can see how you could mistake that. I can make that clear.
Yeah.
So I took sum of the row.
Since we've been doing like column sums and row sums, it might be
Yeah,
nice to differentiate that way.
I can say sum down each column or something. I could also just put x is equal 0 in the parentheses, and people would know what I'm talking about. All right, so let's see how this changes. So much garbage. All right, so here we go.
Okay.
Ta-da.
Here we go. And you can see that the cosine, although one is cosine and one is sine, you really can't see any particular relationship between the two. They're really all basically 2 different random functions. Which is also that's another feature of this, is that basically you can do 2 functions at once. I mean, buy one, get one free. This is the ultimate buy one, get one free. All right, so a lot of neat stuff here, a lot of stuff having to do with complex. I don't know did Dr. Diesel teach Fourier analysis last summer or something?
This summer, you did.
In the summer, did you take it? All right, so did he do complex stuff or mostly real?
We were just going with the heat heat distribution, like in a room or in a solid object or
Okay.
things like that. Basically, it's mostly dealing with heat wave equation.
Okay, but your eigenvectors and eigenvalues were all real things.
Yeah.
So this is related to that. This is kind of one step up. But that's cool. All right. It's neat how all this stuff ties together. I really can't go more into it, but it's just very, very
Yeah,
great.
you could. We'd be here all night though.
So let's see what I want to do now.
Can you save that?
Should I save this as something else? Well, it's already saved. So you're already host. So no, since it's Dropbox, you can recover your old.
But you fixed it, so.
Did you, I saw on Janet's, she had something that got rid of all the junk numbers.
Yes, mine's up there. If you
got
just
it too?
if you do the Control F and search for suppress. There you go.
That's something you need to add into your course.
Okay.
Because that makes reading the imaginary and like a lot of this stuff so much
Okay.
nicer.
All right. Okay. I'll.
Because instead of that e
Yeah.
to the negative 16,
Yeah.
it just says 0.
Okay. All right. Yes, I think so. Yeah. You guys are the guinea pigs.
I'm just saying that,
Yeah.
like I saw that and I was like, holy cow, hers looks so much better than mine.
Yeah. Okay. Okay. Yeah. I definitely need to make some changes there. All right. So let's close this.
He's just going to print all of our old assignments and highlight them and then add all the code in.
And then, let's see. All right, so I don't know why this is.
So I don't know if Jack got that from you.
So I think
Hmm?
I can.
Jack, get that from you?
Which?